I welcome you all to the session of applied thermodynamics, and we shall discuss today about the work ratio, efficiency, then we shall go to discuss about the cycle which are used to analyze the performance of the steam power cycle. Okay. So, if we try to recall, in the last class we have just discussed about several components which are there in a steam power plant. To be precise, though we did not discuss about the minor equipment, but still if we can recall, we have discussed about the major equipment. So, if we try to recall what are those equipment. So, if we write steam power cycle, or I can write steam power plant. Briefly, we will draw this line diagram which we have seen in the previous class. If we give the name, this is 1, this is 2, this is 3 and this is 4, and this is the circuit or this plant is running in a cyclic manner. Okay. So, this is what we have seen in the last class, and we have discussed about the objective of several, at least this 4 major equipment in this circuit. Now, what I would like to discuss today, we would like to discuss today a few index before I go to discuss about the Carnot cycle. Now, this is the line diagram, this is the very simplest what I can say diagram to understand. Now, at least we have understood from the previous class is that when the working substance for this particular cycle is steam water mixture. Now, when the working substance is entering into a particular equipment and when it is coming out from that equipment, there is a process, and those processes we have identified. In a pump, there is rise in pressure of the condensate which is collected from the condenser. The purpose of the pump is having to develop pressure. Now, in a boiler, when the liquid water is allowed to go to the boiler, upon receiving heat from the external source, that is what is shown over here by this Q in, water will be converted into steam, and that steam will be again taken to the turbine, not directly to the turbine, but before steam enters to the turbine, it will flow or it will flow through the nozzle, those are known as flow nozzles. We shall discuss on this particular topic, but I did not show those nozzles over here, and while steam is expanding in the turbine, you can understand the this is turbine and this is condenser. See, Now, you can understand that the schematic though it is schematic depiction, but the turbine shape is kind of diffuser. So, you can understand that while steam is flowing through the turbine, it will expand, and while it is expanding, it does work on the wheel of the turbine, and then we are getting work output, and finally, after doing some work, steam is collected to this particular equipment which is known as condenser, wherein the coolant is circulated and coolant is circulated through this coil, and over the coil steam is allowed to pass, and by virtue of heat exchange the steam is getting condensed into water. We will definitely have different pressure and temperature, and that condensate is again collected at the bottom of the condenser and pumped back to the boiler. So, this is the cycle. Now, if this is this cycle, at least we should know the cycle efficiency, right. Why? Because you can understand we are supplying energy, heat in the form of heat here. Now, this cycle is there even for the nuclear power plant, let me tell you. So, this heat energy for the thermal power plant is supplied by burning coal. If it is diesel fired plant, then definitely the energy will come from the diesel from the fuel. So, whatever may be the case, whether it is coal fired plant or it is diesel fired plant. So, in a thermal power plant, this heat energy is coming from the combustion of the coal. Now upon receiving, so that means we are supplying heat energy, and at the cost of that heat energy you are getting work output, and that is why we need to calculate efficiency, right. So, we can understand that this part is there because we need to run this cycle in a cyclic manner, and as I said in the last class, that second law of thermodynamics puts a restriction that we should have a place wherein heat must be rejected, and that is why this condenser is there. So, what we can understand from here is that we are supplying some amount of energy to the circuit, and at the cost of that energy you are getting some amount of work output, but that is not equal to the energy that we have supplied. So, some part of the energy is getting rejected. So, considering this aspect, we need to know what will be the efficiency, because efficiency is we have seen, we have understood, because we have seen in every place where we need, rather we are having energy conversion, we need to have efficiency. Maybe efficiency can be defined in different from different perspective, but question is efficiency what we have understood from our understanding from our undergraduate different undergraduate courses, that we need to define one index by which we will be able to understand the performance of the plant. So, basically at the cost of that energy, what is the output we are getting, output energy. So, input energy is there. So, out of this input energy, what fraction we are getting as the output energy. So, now I am talking about efficiency, that is very important. So, if we talk about efficiency of the thermal power plant, right. So, this is very important when we analyze cycles. So, this is steam power cycle. As I said in the last class that there are two different cycles, either gas power cycle or steam power cycle. So, whether and that depends on the working substance, whether it is steam power cycle or gas power cycle, we analyze the cycles, and we analyze the cycles because our objective is to predict the efficiency. What I said, that there is a pumping process inside the boiler, also there is a process inside the turbine, and finally in the condenser. So, all these processes constitute together to form the cycle. So, eventually if we consider all these processes will be required to calculate the efficiency of the plant. So, when we are trying to calculate the efficiency of a plant, what we assume all the processes are ideal, right. So, basically what we do normally, we assume all the processes which are there in the circuit are ideal processes. If all the processes are ideal, the corresponding efficiency is called as ideal cycle efficiency. So, there are two different One is called ideal cycle efficiency. So, here we assume all the processes are ideal, but again we have this is the subject where we are applying the concept that we have learned from basic thermodynamics. So, we have understood from the basic thermodynamics course that in a process some degree of irreversibility is there, right. So, though we have just now discussed that to calculate the efficiency of the plant, we assume all the processes are ideal, that is pumping process is ideal, boiling inside the boiler, that is also ideal, expansion of the steam inside the turbine, that is also ideal, and finally condensation of the steam or rather condensation of vapor, and that is also the ideal process. But this is not the case in reality. In practical scenario, there are, rather I can say, some degree of irreversibility will be there in all the processes. If we take if we take those irreversibilities into account, so some degree of irreversibility is there in the pumping process, some degree of irreversibility is there in the boiling process, that is boiling of liquid, some degree of irreversibility is there in the expansion process of the steam inside the turbine, and some degree of irreversibility is there in the condensation, that is the condensation of vapor into the liquid. So, basically if we consider all these irreversibilities, so the ideal cycle efficiency will not be the ideal one. So, we will be getting actual cycle efficiency, and that is what we have learned from basic thermodynamics course as well as you have learned from the fluid machines, that is hydraulic turbine and pumps. So, basically another efficiency that is also known as actual cycle efficiency. And this actual cycle efficiency is coming into the picture because of the thermodynamic irreversibility that is there in all the processes which we have discussed till now. So, this is because of some degree of irreversibility. In all the processes. Okay. So, that is there. Now, so basically we can see that there are two different efficiencies. One is ideal cycle efficiency that we can understand, but considering the thermodynamic irreversibility, we also need to define another efficiency, that is actual cycle efficiency. Now, the ratio of these two efficiencies, that is the ideal cycle efficiency to the actual cycle efficiency, that is known as relative efficiency. Okay. So, basically I am telling for the sake of completeness that relative efficiency, till now we have discussed about two different efficiencies. So, relative efficiency, which is nothing but the ratio of actual cycle efficiency to the ideal cycle efficiency to the actual cycle efficiency. Now, why we need to define this? So, this is nothing but, as I told you, this is ratio of ideal cycle efficiency divided by, or ratio of ideal cycle efficiency to the actual cycle efficiency. So, you can understand this relative efficiency is defined, that means this relative efficiency is a measure of the performance of the power of different cycles of the plant. Okay. So, basically this relative efficiency is a measure of the performance achieved in the cycle, right. Okay. So, this is these two efficiencies, because you should know. Now, what I need to discuss, that just in the previous slide, we have discussed about ideal cycle efficiency. All the processes are ideal. Now, you will be knowing that in many places, so far we have studied fluid mechanics, heat transfer, and also thermodynamics, if we talk about the subjects from the thermal fluid sciences. Now, you have seen in all cases, in all subjects, we do analyze the ideal cases, ideal efficiency. For example, for the hydraulic turbine, again we, if you can recall, we do analyze the ideal efficiency. For the heat transfer case, for the fin efficiency, that is again ideal fin efficiency. So, the word ideal we consider. So, why do we need to consider this particular term? Though we are very much familiar that in real practice the efficiency, output, what we will be getting, those are not the ideal, those are the actual. So, knowing a priori that the efficiency, output, everything will be actual. So, that output will be always lesser than that predicted by any equation, that is the ideal one, but we always study this. So, the purpose is to study the ideal cycle efficiency. Ideal efficiency is to compare the performance of the actual one. So, basically that is there everywhere, even in a class. If you would like to, for the relative grading system, if you would like to give grades to the students whose performance is not very good, but always we need to standardize, we need to compare the performance of a student with the performance of the student who is the topper in the class. So, always we do that. So, basically here also, though it is very difficult to achieve ideal efficiency in practice, but still we do analyze cycles, we do analyze the ideal cycles. The sole purpose is to compare the efficiency of the actual cycles. So, how close we can reach. So, basically if we consider the actual cycle in real practice. So, our objective should be to optimize the cycles, different processes in the cycles, so that we can reach, we won't be able to meet the ideal cycle efficiency, but at least we can reach closer to that. So, that is why this ideal, the concept of ideal cycle efficiency is there. Now, so when we talk about any cycle, so basically for the ideal cycle, so as I said you, we must understand the ideal cycle efficiency, and this is done only to compare the efficiency of the actual cycles. So, for the we have studied in classical thermodynamics that there are many ideal cycles, but the Carnot cycle is considered first and then other cycles are considered. Accordingly, if we among the ideal cycles, Carnot cycle is considered first. So, if we now consider the ideal vapor cycle or ideal steam cycle, then again Carnot steam power cycle or Carnot vapor power cycle will come first. So, now if we try to compare that ideal, so if we write over here ideal cycle, so the Carnot cycle is considered first, and similarly ideal steam power or vapor power cycle to compare. So, basically this is the cycle which is steam power cycle, but sometimes it is also known as vapor power cycle. So, basically if ideal Carnot cycle, if the Carnot cycle is considered first, then ideal vapor cycle should be Carnot vapor cycle. We shall discuss on this about the cycle, but at least before I go to discuss about the cycle, you have all studied in thermodynamics, but just only to recapitulate whatever we have learned, I will discuss. Now, before I go to discuss this topic, it is essential to know that okay, we are talking about ideal cycle efficiency. So, basically if we consider, rather if we think that there is a steam power plant. So, basically if you like to know what will be the efficiency of the plant, there are two different aspects. One is the capital cost, or which is also known as initial cost, and other is the operating cost. So, basically you can understand when you talk about efficiency, we understand. So, operating cost, that means you can understand we need to supply energy. So, we need to burn coal. So, for that is operating cost. We need to supply coolant to condensate to reduce the temperature of the steam which is coming out from the turbine, right. So, in all these cases we are having operating cost. So, all these costs should be combined together to understand what is the operational cost. So, operational cost is an indirect measure of the efficiency that we are talking about, right. So, to operate this system, to run this system, there are here we are having input energy, here we are having circulation of the coolant, we are also having work input to the pump. So, basically operational cost which is associated with the operation of this pump, operation of this condenser, operation of this turbine, operation of the boiler, right. So, operational cost is there. Also the capital cost or initial cost is there. So, initially we need to install pump, install boiler, install turbine, install condenser. So, depending on the size of the plant, how much work output we need from this particular plant, this capital cost or initial cost will be depend. So, basically when we will talk about, when we will consider a particular cycle, that then this choice depends on two important aspects. One is called capital cost or initial cost, other one is called the operational cost. So, if we quickly review that, one is called capital cost, or it is also known as initial cost, and second one is operational cost, to operate, to run the cycle. So, now that is very important. Now, there are, so we have understood what is capital cost and what is operational cost. Now, we should again understand that there are there are index, right, rather I can say there are indices which are used to define the cost that will be associated with the capital one and the operational one, right. So, we have understood that if you would like to if you would like to get output from a steam power plant, depending on the amount of work that we get from this plant, size of the plant will depend. So, capital cost is depend on the size of the plant. So, size of the plant will dictate the capital cost, and once it is there, then to operate it, this we have discussed that another cost will be there, and that is the operational cost. So, basically these two costs we have understood. Now, the capital cost and operational cost, they quantify what will be the operational cost and what will be the capital cost. To quantify these two costs, again there are indices which are used. One is known as work ratio or back work ratio. So, these two terms will be defined, we will define now. what is work ratio and then what is back work ratio. See, just if we look at this schematic, you can see that we are getting work output at the cost of this heat input that is given to the boiler. Now, this work output is not only the work output, right. So, the net work output is something else, because a part of the work output is getting or is consumed by this pump. So, we are getting work output from the turbine, a part of which is getting consumed by, is consumed by the pump. So, the net work output is not the W out. So, the net work output is nothing but something that we will discuss, but in this circuit what is the positive work? So, if we think that this is the positive work we are getting, but this work can be viewed as the negative work that is being supplied to the cycle. So, this is the amount of work we are getting from the cycle, while to get this cycle, to get this work output, we also need to give this work as the input work to the cycle. So, this work can be viewed as the negative work. So, that means total work, the net work by the positive work is known as work ratio, RW. So, this is work ratio. Right. So, this is work ratio. So, that means this work can be viewed as the positive work, that means we are getting from the cycle by doing this, because installing this plant, that is capital cost, also by running this plant we are getting this amount of work, that is the positive work. So, this work is not the positive work. So, this is the work we are getting as a positive work, but this is not the net work. So, this is the positive work and this is the negative work. So, the net work by positive work, the ratio of these two quantities are known as work ratio. So, basically you can understand this RW can be written, what is net work, that is W positive minus W negative by W positive. Okay. So, if we go to the next slide, so this work ratio RW can be written 1 minus W negative by W positive, right. So, this is the work ratio. You can understand that the negative work, the ratio of negative work to the positive work is a decisive factor for the thermal efficiency of the plant. So, we are supplying energy, at the cost of this energy you are getting work output, but that work output is not, this is not the net work output, though it is positive work, but this is not the net work, right. So, work which we are getting from the turbine, though it is the positive work, because this work can be viewed as the positive work, because we are getting from the cycle itself, and this is the negative work because we are giving to the cycle. So, basically though it is positive, but that is not the net. So, basically what we can understand from this, that ratio of negative work to the positive work, which is the decisive factor for the efficiency of the plant. Now, the ratio of this quantity is also known as back work. So, this is known as back work. Back work ratio, right. So, you can now just I would like to discuss two important points for this particular case, that if we go back to the cycle, if the work which is being supplied to the pump for the operation of the cycle is a significant part of this positive work, then definitely what will happen, again I am telling, if the input work, that is the work which is being supplied to the pump for the operation of the cycle, is a significant portion of the positive work which you are getting from the turbine, then what will happen, this quantity will be high, and then the efficiency of the plant will be lesser. So, basically you can understand, if W negative is a significant part of the positive work, then RW will be less. So, it will be lesser when high, right. So, basically if W negative is high, that is significant part of the positive work, that back work ratio will be high. So, can't we write that back work ratio or RBW? So, we can write back work ratio RBW, that is nothing but 1 minus RW, that we can write from this expression. So, if this amount is significant part of this positive work ratio will be less. If this becomes higher, work ratio will be less, back work ratio will be high. So, that is quite obvious. So, work ratio is less, back work ratio will be high. Now, if work ratio is less, then you can understand what will happen, efficiency of the plant will be lesser, right. So, what I would like to discuss, that very important point I would like to discuss. Now, you will be understanding that ideal cycle efficiency, right. So, why this, when this negative work will be a significant portion of this positive work, if the irreversibility associated in this pumping process, irreversibility associated to this pumping process is very high. So, if some degree of irreversibility will be there in this in the pump to execute when the pump is executing the process. So, that means the process which is there in this particular device, if the amount of irreversibility is very high, then this work input we need to provide more work input, right. So, the W in will be, W negative will be definitely a significant part of the positive work when some degree of irreversibility associated to the pumping process is very high, right. If that is the case, you can understand, now you can understand that when we talked about ideal cycle efficiency and actual cycle efficiency, ideal cycle efficiency when we have defined, we did not take into account the degree of irreversibility, right. So, if we consider the degree of irreversibility, then actual cycle efficiency is there. Now, and that too depending on the degree of irreversibility, actual cycle efficiency will depend. So, if the degree of irreversibility is more, actual cycle efficiency will be less. So, what we have defined, what we have understood, that when this back work ratio is more, that is negative work is a significant portion of this positive work, then the degree of irreversibility associated to the pumping process is high, then definitely it is not this ideal cycle. So, degree of irreversibility is there, so that is definitely actual cycle, and that too if the degree of irreversibility is high, actual cycle efficiency will be less. So, basically what I would like to conclude is that this higher the back work ratio, actual cycle efficiency will be less. It does not matter whether the ideal cycle efficiency is less or high. I hope you have understood. So, what I would like to tell you, when the back work ratio is very high, work ratio will be less, then so when RBW is high, RW will be less, then consequence is actual cycle efficiency will be lesser, right. So, basically that is the case. So, if back work ratio is high, work ratio will be less, actual cycle efficiency will be less. Now, we have written here the actual cycle efficiency will be lesser, but we did not talk about whether the ideal cycle efficiency will be lesser or higher. So, ideal cycle, it does not matter whether the ideal cycle efficiency will be lesser or higher. So, our objective should be always to obtain higher work ratio and lesser ideal cycle efficiency. Right. So, this is the case. So, our objective should be to always obtain higher work ratio. For that, whether the ideal cycle efficiency is less or high, that we should not have botheration, rather we should only be careful to obtain higher efficiency, actual cycle efficiency. If you would like to have higher actual cycle efficiency, we should have higher RW. So, that is the work ratio should be higher. Okay. So, this is one index to compare to see the performance of the plant. So, as I said that ideal cycle efficiency and actual cycle efficiency, but at least to quantify those there are these two different indices, one is the work ratio and back work ratio that we have already defined. Another is known as specific, another index specific steam consumption, SSC, right. So, this is another important index which is used for the comparison of the steam power cycles, is this specific steam specific steam consumptions or sometimes specific steam rate, right. The steam rate. Okay. So, basically what is specific steam consumption, SSC, or steam rate? So, this is another important index which is used to compare the performance of the steam power cycle. What is this? So, this specific steam consumption is the what is the definition, because we should understand what is the definition, right. So, this is nothing but mass flow rate of steam, mass flow rate of steam per unit, that is kilowatt hour power developed. Right. So, this is basically mass flow rate of steam per unit power developed. So, again you can see I will be discussing these two again about these two indices again. So, what is SSC? So, if we write this SSC, that is specific steam consumption, that is nothing but 1 by W net kg per kilojoule, right. So, that is mass flow rate of steam per kilowatt hour power developed. So, this is 1 by W net. Now, if we can write what is kilojoule, that is kilowatt second. Now, I mean if we go to the next slide, or rather I can write over here, that is 1 by W net kg kilowatt second, but this is the specific steam consumption. So, mass flow rate of steam, but we have to define per unit power which is kilowatt hour, not kilowatt second. So, that is nothing but 3600 kg divided by W net kilowatt hour, right. So, we have to define mass flow rate of steam per unit power, but in the form of kilowatt hour. So, from this at least we have been able to arrive here, that is nothing but 3600 by W net kg per kilowatt hour. What we can see from this expression, as I said, this is again another important index which is used to compare the performance of the steam power cycle. So, you can understand higher the SSC, less will be W net. If W net is less, then what will be the consequence? Consequence will be the efficiency will be less, right. So, if we get if W net is less, right. So, if W net is less, then work ratio will be less. If work ratio is less, efficiency will be less. So, that means here higher the SSC, that means what do you mean by higher value of SSC? So, mass flow rate of steam will be high. So, that will depend, again I am telling. So, if I go back to the schematic depiction, if you need to ensure that the work output, that means the electricity that we demand from this particular plant should be very high, then the plant size will be high. So, if you need to ensure that the work output from the plant will be very high, then the plant capacity, plant size will be very high, which in a way indicates that the SSC will be high. So, if SSC is very high, then we have seen that W net should be less. So, higher the capital cost. So, if you would like to have bigger plant, higher capital cost, then W net will be very small and efficiency will be less. Now, if W net is very, when SSC is very small, W net will be very high. So, you can understand this is an important index which govern both the capital cost as well as the operational cost. So, it is very important that we should understand. So, higher the SSC, less will be W net. If less is the W net, efficiency will be less. So, if you need to maintain the same efficiency, then operational cost will be high. So, for the bigger plant, higher plant, so higher the SSC, W net will be less. So, basically I mean if we do not, if we provide the same heat input, but we would like to get what I am telling. So, thermal efficiency will be less. So, for this particular case, we have understood that this parameter is very important. It governs both the capital cost as well as the operational cost. Okay. So, for the same heat input, if this is bigger, then what will happen? This will be less. So, this will be less, that means thermal efficiency will be less. So, this is very important to understand. Now, very quickly we will be going to discuss that, at least we have discussed about work ratio and efficiencies, and we have understood that there are two indices, one is work ratio and SSC, specific steam consumption, which governs both the capital cost as well as the operational cost. Okay. Now, we will shall quickly discuss about the Carnot cycle. So, as I said, this Carnot cycle, to be precise, Carnot vapor cycle. Okay. So, as I said that there are two efficiencies, one is ideal cycle efficiency, other is the actual cycle efficiency, we have seen, but again I am telling, though it is very difficult to achieve the ideal cycle efficiency in practice, but still we need to analyze it, because we need to compare the performance of all actual cycles. If you would like to compare actual cycle, at least we should have one index by whom we can consider, we can compare with. So, basically to compare the actual cycles, at least we should have one cycle, and that is the ideal cycle, and for that we should understand this. Though you have studied this in thermodynamics, but I am trying to recapitulate. What is Carnot cycle? That is the ideal cycle considered first, right. So, there are two isothermal and adiabatic processes. So, two reversible and two adiabatic processes are there. So, this cycle is having two isothermal of course reversible and two adiabatic reversible processes, right. So, if we try to draw the TS and HS diagram, say we will consider this line diagram and we have 1, 2, 3, 4 different points. If we now try to map the processes, all these processes corresponding to this particular schematic diagram in these two planes. So, so now if we consider this TS diagram, so here we have, so the process, if we try to understand 1 to 2, that is the we can see that this is the constant pressure, though. So, now you understand this is constant pressure boiling. So, pressure is remaining constant, but temperature increases from 1 to T2. So, here you can see that the temperature increases from this T1 to T2 and this is isentropic process, that is reversible. So, basically two reversible isothermal, reversible adiabatic. So, you can understand two reversible isothermal process 2 to 3 and 4 to 1, constant temperature heat addition and constant temperature heat rejection, that is what we have studied. So, this is basically heat Q out and this is basically W net. Here we have shown the point 2 and 3, the points 2 and 3 are shown on the saturated liquid line and saturated vapor line, but for the sake of generality these 2 points could be shown to be inside the vapor dome, right. So, although I have shown these 2 points on the saturated liquid line and saturated vapor line, but for the sake of generality these 2 points could be shown to be inside the vapor dome. Okay. So, now what this is the now what is the HS diagram? So, this is 1 2 3 4. So, you can understand that this is x 4, right. So, you can understand these are this is, so this is the HS diagram you can understand. So, this is P 3 is equal to P 2 and this is P 4 is equal to P 1. Okay. So, what I would like to tell you, although you have studied two reversible isothermal, two reversible adiabatic processes which are shown in this TS and HS plane. Now, I have shown the points 2 and 3 on the saturated liquid line and saturated vapor line respectively, but now at least we should discuss. So, if we consider, then it can be shown that efficiency of the plant can be written in terms of the 1 minus TL by TH, that I can derive now very quickly. So, you can understand. So, if we try to discuss about the efficiency of the plant. So, this is x 1. Now, so what are the different processes? Again I am telling, just I have tried to represent all the processes which are there in the cycle in the TS and HS plane. So, 1 to 2, this is the process in which heat is added, right. So, 1 to 2, that is the process in which heat is added to heat addition. So, if I try to write per unit mass, that is QL, that is nothing but H 3 minus H 2, and work input. So, this is process 2 to 3. Work input process 1 to 2, right. So, this is W in, let me write this is W in. So, this is, so that is minus H 2 minus H 1. So, I have given negative, that is the negative work that is given into the system. Now, that is work output process 3 to 4, that is W out, that is H 3 minus H 4 and heat rejection. That is process 4 to 1 cube, this is cube H and this is Q L, that is minus H 4 minus H 1. So, again this is rejected. So, I am writing following the convention of the first law of thermodynamics, I have written this negative sign. I am not going to, so I have straightway written this equation. Perhaps Professor Sahu has discussed about the basic laws to describe these, I mean that those will be required very much to understand the subject, the content of the subject. So, if we apply steady state steady flow equation applied to the boiler, condenser, turbine and pump, as I said you in the beginning in the last class that all these devices either heat interacting or work interacting devices. So, if we apply the steady state steady flow process applied to the boiler, pump, compressor, boiler, pump, turbine and condenser, we will be getting, we can write this expression fine. So, basically now what I will do, my objective is to calculate the efficiency, though it is, since it is ideal cycle. So, efficiency that we will be getting by from this expression, from this exercise, again that will be the ideal cycle efficiency. So, you can understand from the TS plane itself. So, the area which is shown by this hatched portion shown by the green color, that is the Q out. So, the hatched portion shown by this red color, that is the W net. So, I can we can calculate that is the Q in, what the W net by Q in, that is the efficiency. So, if we try to calculate the efficiency, thermal efficiency of the Carnot cycle, eta Carnot, so that will be equal to W net by Q in, that is the thing. Now, what is W net? W net will be equal to, you can understand, we are having work output minus work input. So, this minus this, that is the W net. So, H 3 minus H 4 minus plus H 2 minus H 1. So, this would be minus, right. So, that would be minus, I have to erase it again. So, minus, okay. So, you can write, you can understand, we can write this is H 3 minus H 2 minus H 4 minus H 1. Why I am doing this? Now, you can understand this H 3 minus H 2, that is Q H, and H 4 minus H 1, that is Q L. So, this is nothing but Q H minus Q L. Okay. So, now what we can write, that H 3 minus H 2 minus H 4 minus H 1 divided by Q in. What is Q in? That is QH, that is H 3 minus H 2, H 3 minus H 2. Now, so this Q in for this particular case equal to QH. So, we can write 1 minus H 4 minus H 1 divided by H 3 minus H 2, right. So, this is the expression of the Carnot cycle efficiency. Now, you can understand what is H 4 minus H 1, that is nothing but QL. So, this is nothing but 1 minus QL by QH, right. So, eta Carnot, if we consider this, that H 4 minus H 1 and this is H 3 minus H 2. So, you can understand this process is basically these two processes are isothermal process. So, we can write this is 1 minus TL by TH. So, you have studied from the thermodynamics course. So, this efficiency is also given by 1 minus TL by TH, that is the ideal cycle efficiency. Okay. Now, question is I would like to take another 5-6 minutes to discuss that you have seen that in this particular case, as I said you that these points 2 and 3 are shown on the saturated liquid line and saturated vapor line respectively. Now, as I told that for the sake of generality these 2 points could be shown to be inside the vapor dome. Now, what we can see from this process 2 to 3, that is there is a phase change, right. So, saturated liquid is getting converted into saturated vapor. So, when there is a phase change, also you can see from point 4 to point 1. So, when there is a phase change, the in a vapor cycle, these two isothermal processes, that is process 2 to 3 and process 4 to 1, can easily be, rather I can't say like this. So, when there is a phase change in a vapor cycle in two different processes, one is process 2 to 3, another is process 4 to 1. So, these two processes are isothermal processes, these two processes are easily attainable as the internally reversible process. So, again try to understand, when there is a phase change in this particular following this particular cycle, that processes 2 to 3 and 4 to 1, there is a phase change in the vapor power cycle. These two processes which are the reversible isothermal processes, we have discussed, we have said. Now, these two processes are easily attainable as the internally reversible cycle, but mind it, to convert saturated liquid into saturated vapor, we had to supply heat, that is transfer of heat externally for this boiling, as well as we had to take out heat from point 4, and that is why this condensation takes place. So, heat transfer externally to the system from the system for the boiling and for the condensation are highly irreversible process. So, basically though these two processes are internally reversible phase change process, but they are not externally reversible, that you have studied in thermodynamics. Okay. Now, very quickly I will discuss a few important points, and that is known as limitation of the Carnot cycle. So, now this is ideal cycle, as I said, again I am telling that this Carnot cycle is the ideal cycle. Ideal cycle, it is very difficult to implement in practice, it is very difficult to achieve in practice, but still we need to study it, as because all the actual cycles will be compared with this ideal cycle. So, Now, at least time has come to understand, time has come to see what are the limitations, what are the drawbacks associated to this particular cycle. So, you can understand, one is that I told you that these processes are reversible, though we have said, but maybe these processes are internally reversible, but externally supplied heat from the external source to the system and heat transfer from the system to the surroundings because of the boiling and condensation, these two processes are not externally reversible. One important, so basically what are another, in addition to this there are several other issues. First of all, see the condensation point, condensation process, you can understand the condensation process starts from point 4 and it is getting terminated at point 1. So, it is very difficult that the amount of heat that should be taken away from this from this process, that the condensation process will terminate at point 1 and that is called partial condensation. It is not that the liquid which will be getting saturated liquid. So, at point 1 it is two phase mixture, it is not the saturated liquid and that is partial condensation. So, it is very difficult to design the condenser which will allow us to have this partial condensation and the condensation process will terminate at point 1, number 1. So, that is called, number 1 is partial condensation. Difficult to design condenser, right, we have understood. Again I am telling, because this is not really achievable in practice. In practice we have to design condenser. So, if we cannot design condenser which will be efficient, which will be efficient, rather which will work efficiently to have this partial condensation, that is really difficult. Number 2 is that, see this process 1 to 2, that is what we have seen from the schematic depiction, that is pumping process, but pump cannot handle two phase mixture. So, we should have a compressor. So, pump cannot handle two phase mixture. So, instead of a pump, if you would like to design a steam power cycle following the Carnot cycle, we must have a compressor. But when we are designing a compressor to handle this two phase mixture, power consumption will be very high. So, the power consumption will be very high, that means the work input to this compressor will be a significant portion of the work output. So, eventually we will be getting high back work ratio, low work ratio, right. So, this is another important drawback. So, that is high power consumption, and it is having two different problem. Number 1 is designing a compressor, I will be discussing that too. Another is high power consumption. So, W net will be significant. Eventually, we will be getting low RW and high RBW, right. I did not write anything on this designing a compressor. So, basically till now we have understood that lower work ratio and high back work ratio. Last point is that, see, though we can run a compressor even compromising that efficiency of the cycle. So, low work ratio, high back work ratio, that means efficiency will be very less. It is quite obvious, because the power required to operate the compressor will be a significant portion of the work output. On the top of that, it is again very difficult to design a compressor which will take two phase mixture at its inlet and it will give saturated liquid at the outlet. So, you understand, following the Carnot cycle, if we design a compressor and the process will be 1 to 2. So, at the inlet to the compressor we can quality will be 2 phase mixture, but at the exit of the compressor the liquid will be saturated liquid. So, again it is very difficult to design. Designing a compressor is difficult which will supply saturated liquid, right. So, you can understand, and so basically this is the these are the thing, and finally let me write over here is that you can understand again if we try to design a steam power cycle following this Carnot one, following this Carnot cycle, that is ideal cycle, the quality of the steam at the exit of the turbine is 4. So, it is again 2 phase mixture inside the vapor dome. So, if the quality of the steam is very poor, so the steam which is coming out from the turbine is having high moisture content, and that will lead to erosion or blade pitting of the turbine. So, turbine blade pitting and turbine blade erosion. So, this is again very difficult. So, the quality of the steam at the exit of the turbine which is dictated by this 0.4. So, this is the expansion process, and this is the 3 to 4, that is the expansion process. Now, for the poor quality, the moisture content of the steam at 0.4 is very high, which will lead to another important problem, that is called turbine blade erosion. So, basically I am writing quality of steam at 4 is poor, and it will lead to turbine blade erosion. Okay. So, these are the different drawbacks we have identified, and to overcome this drawback we need to have modification of the Carnot cycle, and eventually we need to go to the actual cycle. So, those actual cycles we shall now discuss one by one and from the next class onward. Thank you.